in previous lectures, we discussed the Maxwell's equations and the boundary conditions. Now we investigate the solution of the Maxwell's equations. Let us take a simplest possible problem, that is, if we consider a medium which is completely source free, that means there are no charges, there are no currents, and if the medium is unbound, then we can ask a question: in what form the electric and magnetic fields would exist in this medium. At this point of time, we defer the question of how the electric and magnetic fields would be generated in a medium. Let us assume somehow we have got electric and magnetic fields, and then we can ask the question, what would be the relationship between the electric and magnetic fields in this unbound source free medium. We also believe that the solution which we get from this equation will be the simplest possible solution which is consistent with these equations. So we believe that the nature follow the simplest possible path which is consistent with the constraints. What I mean by this is that we look for a simplest solution which is consistent with the constraints. If I take a simple example, that if the function was known at one point, then the simplest solution would be the function constant passing through that point. If I know the function value at 2 points, then it would be the linear function passing through these 2 points, and so on. Of course, when we have 2 points, there are infinite functions which can pass through these points. However, as we said, we will accept the simplest solution, which will be the linear solution, which is consistent with the values of the functions at these 2 points. Precisely the same thing we are going to do for solution of the Maxwell's equations. That we take the simplest solution, ask whether this solution is consistent with the Maxwell's equations. If it is not, then we increase the complexity of the function and then see whether the function becomes consistent with the Maxwell's equations. So now let us consider a medium which is unbound. So we are now investigating a medium which is unbound. That means there are no boundaries, there are no boundary conditions to be applied. So the medium is unbound. Also assume the medium is isotropic. That means the permeability and permittivity of the media are scalar quantities. We also assume that the medium is homogeneous. That means the medium parameters like permittivity and permeability are not functions of space, and we also assume that there are no charges and currents in the medium. So we have epsilon and mu which are not functions of space and direction. The homogeneousness is not a function of space. The isotropic nature is that these quantities are not function of direction. Then we assume there are no sources. So the charge density, which is rho, is equal to 0 in this medium. Also the current density is 0. So we have J is also equal to 0 in this medium. Then we can write the Maxwell's equations under this constraints, and that will be del dot D, that will be equal to 0 because there are no charges now. So the volume charge density is 0. Del dot B is always 0. Del cross E is minus dB by dt, and del cross H, that is equal to, since J is 0, it will be d by dt. Now using the constitutive relation that B is equal to mu times H, and since mu is scalar quantity, it is isotropic. So, H and B are in the same direction. Similarly, D is epsilon times E, epsilon also is a scalar quantity. However, the mu and epsilon, the medium which we are talking about is the unbound medium. So, this medium is similar to like free space. However, the permittivity and permeability for the free space are denoted by epsilon 0 and mu 0. Let us consider a hypothetical medium which is unbound, but not necessarily free space. So, we are saying that if the medium had some permeability mu, permittivity epsilon, but there are no boundaries to this medium, what would be the relationship between the electric and magnetic fields in that medium? And then by substituting mu equal to mu 0 and epsilon equal to epsilon 0, we can get the solution corresponding to the free space. So, once I substitute into that, and mu and epsilon are also not time varying, so these equations can be written as minus mu dH by dt, and this will be epsilon dE by dt. In electrical engineering, invariably we solve the problems for the periodic signals, and a periodic signal can be decomposed into its Fourier series. So, essentially, if you find out the behavior of a system for a sinusoidal signal, we can always find the response of the system for any periodic signal. So, let us assume, without losing generality, that we investigate the problem here for the time harmonic fields. That means the electric and magnetic fields both are sinusoidal functions of time. So, E and H both vary as a function of time as e to the power j omega t, where omega is the angular frequency of the electric and magnetic fields. For this time harmonic field, then the time derivative will be multiplying this quantity by j omega. So, any time derivative which we have in these equations, d by dt, can be replaced by j omega. So, a time derivative is equivalent to multiplying that quantity by j omega, and the second derivative d2 by dt square is equivalent to j omega multiplied by j omega, that is equal to minus omega square. So, all the time derivatives which we have here in this can be now converted by multiplying this quantity by j omega. So, this quantity now can be minus j omega mu times h, this will be j omega epsilon times e. So, for the time harmonic case, then we can write down the equations, which is del dot d equal to 0, and again substituting for d equal to epsilon times e in these equations and b equal to mu times h in this equation. And since mu and epsilon are not functions of space, they can be taken outside the del sign. So, we can now finally write the equation del dot d is equal to del dot epsilon times e, that is equal to epsilon del dot e should be equal to 0. And since epsilon is not equal to 0, essentially del dot e is equal to 0. Similarly, for del dot b is equal to del dot mu times h, that is equal to mu into del dot h, that is equal to 0. And since permeability is not 0, essentially del dot h should be equal to 0. Del cross E now is from here, if I substitute now for time derivative that is equivalent to multiplying by j omega, this equation is minus j omega mu into h, and del cross h, that is equal to j omega epsilon into E. So, for an unbound homogeneous medium, essentially the equations which we have, the Maxwell's equations, that is del dot E is equal to 0, del dot H also is equal to 0, del cross E is minus j omega mu H, and del cross H is equal to j omega epsilon E. So essentially now we are looking for solution of these equations, specialized equations for this unbound medium. Now if I look at these two equations here this is the space derivative of the electric field is related to the time derivative of the magnetic field. This equation, if I recall, is similar to what we had got for transmission lines. In transmission line, if I replace electric field by the voltage and magnetic field by current, then in transmission line I had derivative of voltage was equal to minus j omega L times current. So mu, which is permeability, it has units Henry per meter, electric field is having volts per meter, H is amperes per meter. So if I take that per meter out, then this will be volts, this will be Henry, and this will be amperes. So this equation is identical to equation which we got for the transmission line. Exactly similar thing is here. This is the space derivative of with the current that is related to j omega epsilon. So it is like a capacitance multiplied by the voltage. So as we got the equation in case of transmission lines, the coupled equations for voltage and current, this is essentially the generalized form of those equations. So here we are having in general 3-dimensional space. Also we are having quantity here electric and magnetic fields which are not scalars as we had in case of transmission line. So we have this vector quantities which have a behavior in 3-dimensional space. So the space derivative is now denoted by the del operator. So transmission line case which we have discussed is the special case of this generalized 3-dimensional case. Also, as we had noted at that time when we were analyzing transmission lines, that these equations are coupled equations. So here electric field is related to magnetic fields and magnetic field is related to electric fields. So if you want a solution for the electric and magnetic fields, we have to decouple these equations. And if you recall, in case of transmission lines, we had done that by taking derivative of each of these equations and substituting from another equation, we could decouple the equations. Same thing essentially we have to do in this case also. Of course, the derivative operation now will be in terms of this del operator. So we have to appropriately take that operation, but principally we have to take a derivative of this space derivative of these equations and substitute from other to get the decoupled equations. We should also note at this point that these quantities are the vector quantities, and that is why when we define here the space derivatives, we should ask what is the meaning of this space derivative now, because this quantity is a vector quantity. In case of simple scalar functions, the derivative was d by dx or d by dy or d by dz. However, when I am now talking about the space derivative in 3-dimensional space, I can operate space derivative on this, which could be like a divergence operation, or I can operate on this which could be like a curl operation. So one possibility, I take divergence of this quantity on both sides like a space derivative, but if I do that, then this will be del dot del cross H, which will be identically 0. So this will be del dot H, this will be equal to 0 because mu is not equal to 0, omega is not equal to 0, which is the same equation as this equation. So if I take divergence of this equation, then I will get del dot H equal to 0, which is same as one of the equations which you get from the Maxwell's equations. Exactly same thing if I do on this, if I take del dot del cross H, that will be equal to 0. So I will get again del dot E equal to 0, which is same as these equations. So by having a divergence operation on this, we do not get anything new. we simply get the set of equations which we already got from the basic Maxwell's equations. So, we can take curl of this equation. So, if I take a curl of this equation, let us say I take the curl of the first equation, which is del cross E, I get del cross E, that is equal to minus j omega mu times del cross H. We can substitute for del cross H from the second equation from here, and also can use the vector identity to expand the triple cross product, which is del dot E minus del square E, that is equal to minus j omega mu, and substitute for del cross H, which is j omega epsilon into E. Now, for this medium, which is the homogeneous medium and charge free medium, del dot E is identically 0. For this particular case, this quantity is 0. So, this quantity is 0 in this case. So, I get the equation now finally, which is del square E, that is equal to minus omega square mu epsilon into E. If I had done the identical things on the second equation, that if I had taken the curl of this and substituted for del cross E from this equation, I get again the identical equation for the magnetic field, and that is del cross H is equal to minus omega square mu epsilon into H. So, we have now the equations which are decoupled equations. So, this equation governs the electric field, this equation governs the magnetic field, and both equations are identical equations. Again, if you recall, exactly similar equations we had got in case of transmission lines. There also the voltage and current was governed by the same differential equation. So, here also we have a differential equation which is identical. There these equations were single equations because the quantity, the voltage and current, they were the scalar quantities. So, this equation represented one equation, this equation represented one equation. However, in this case the electric and magnetic fields are vector quantities. So, each of the equations consists of 3 equations corresponding to the components of the electric and magnetic fields. So, what that means is that each component of electric field Ex, Ey, Ez in Cartesian coordinate satisfy this equation. The 3 components of H, Hx, Hy, Hz satisfy this equation. And del square operator, as we know, is a scalar operator. So, essentially we can decompose the electric field in each of its components, and every component of the electric and magnetic field must satisfy this equation. This equation, recalling that the similar equation we had for transmission line, and a solution of that equation physically used to represent a phenomena like wave kind of phenomena. These are the generalized form of the wave equations. So, we have this is the wave equations. In the 3-dimensional space. So, essentially what we are now interested is the solution of the wave equation in the 3-dimensional space for a time harmonic fields which are having frequency omega, and for a medium which is having permeability mu and permittivity epsilon. That is the problem now. Now, as we mentioned earlier, we want to proceed from the simplest possible solution and ask whether the solution is consistent with these equations that is the set of Maxwell's equations, and also this wave equation which you have derived from the Maxwell's equations. So, at the moment, since we do not have any idea about the solution, let us check whether the simplest possible solution, which is the constant solution in 3-dimensional space, will be consistent with these solutions. So, you can consider case 1, that the electric, let us look for the solution for the electric field to start with, and the similar arguments will be valid for the magnetic fields also. So, let us say that the electric field is uniform in the 3-dimensional space. So, case 1 is uniform E in space. That means your electric field E is given as some constant k0. E to the power j omega t is always implicit in all these quantities which we are defining. So, as and when we require instantaneous values, we can multiply these quantities by e to the power j omega t. If this is a solution is consistent with the Maxwell's equation, it must satisfy the wave equation which you have derived. So, I can substitute for E equal to constant in this equation. Since E is constant, its del square is 0, these are second space derivatives. So, essentially what we get is del square k naught, that is equal to minus omega square mu epsilon into k naught. And this quantity is 0. So, we have here omega square mu epsilon k naught, that is equal to 0. Since we are now interested in time varying fields, the omega is not equal to 0, mu and epsilon are not equal to 0 anyway. So, the quantity which has to be 0 is k naught equal to 0. So, what this implies that k naught should be identically equal to 0 for this, or in other words, it means that a uniform electric field in 3-dimensional space is not consistent with the wave equation, is not consistent with the Maxwell's equations. So, if you are talking about a time varying fields, then a uniform time varying field in 3-dimensional space cannot exist. One can then go to the next level of complexity, that if the field is not uniform in all 3-dimensional space, can the field which is uniform in one plane be consistent with the Maxwell's equations? So, one can ask, take the case, second case, that E is uniform in not 3-dimensional space, but uniform in a plane. So, E is uniform in a plane. Without losing generality, let us assume that we orient our coordinate system in such a way that the electric field is oriented in x direction. So, up till now we have not defined which way the coordinate system is and which direction the electric and magnetic fields are oriented. So, we have a freedom to choose the coordinate system, and we decide to choose the coordinate system such that the x axis of the coordinate system is oriented in the electric field direction. That means, by our choice, the electric field is given by some constant E0, which will be oriented in the x direction. This is the scalar quantity, and I can put a unit vector which is in the x direction. So, this is the quantity now which is representing the electric field which is oriented in x direction. And now we have to choose, we are assuming that the E is uniform in a plane. Once the E is oriented in x direction, there are two possibilities, that E is constant in a plane which is containing the x axis, or it is constant in a plane which is perpendicular to the x axis. That means we are assuming that the electric field is constant in a plane perpendicular to its direction, or electric field is constant in its plane. So, in this case we are having two choices, considering the plane which is perpendicular to this, and that will be yz plane, or any plane which contains the x axis. So, we can have the plane which could be xz plane or xy plane. So, variation of the electric field in yz plane is one possibility, is variation in the xz plane or xy plane is other case, and these two cases are similar because now the plane is passing through the x axis. So, if I consider now a case that the electric field which is oriented in x direction is constant in a plane containing the x axis. So, let us say I consider that the electric field now is varying in the x direction, in the direction of its orientation. So, let us say this quantity now is only a function of x. So, electric field is oriented in x direction and we are assuming it is varying in x direction. If this field is a solution of the Maxwell's equation, it should be consistent with the Maxwell's equations. So, we can take any of the Maxwell's equation and substitute this electric field in that. So, let us consider a equation del cross E that is equal to minus j omega mu into h. We can write down this curl. So, it is x, y, z. Let us write down this in the Cartesian coordinate system, which is easier to write. D by dx, d by dy, d by dz, and we have this quantity now E, which is only x component, which is E0 x. So, this is E0 function of x, 0 0, that is equal to minus j omega mu into h. Now, since we have assumed that the field is not varying in y and z, it is only a function of x, the derivative with respect to y and z are identically 0. So, in this case we also have d by dy is identically 0, d by dz is identically 0. So, if I substitute into this the equation x y z d by dx 0 0 E0 x 0 0, that will be equal to minus j omega mu into h. Now, this determinant is 0. If you solve this, you will get all the components equal to 0. So, what that means is that for this field which was oriented in the x direction and was constant in a plane perpendicular to that, so it does not have any variation in this direction. For this field, the minus j omega mu into h is identically 0. So, this gives me that j omega mu h is equal to 0. Again, since the frequency is not 0, we take time varying fields. So, omega is not equal to 0, mu is not equal to 0. So, essentially it means the magnetic field is equal to 0. So, this gives me that for this field which is oriented like that and is constant in this plane, for this electric field the magnetic field has to be identically 0. So, that means this is the electric field which will exist without any magnetic field. However, as we know from our Maxwell's equations that the electric and magnetic fields are coupled. So, if the magnetic field does not exist in time varying case, the electric field also cannot exist. So, since there is no H in this case, the electric field also cannot exist. So, this field has to be identically 0. So, what we conclude in the second case that if the electric field is uniform in a plane perpendicular to its orientation, then this field has to be identically 0, because this field says that the magnetic field will be identically 0. So, now we have a second conclusion, that a electric field which is uniform in a plane perpendicular to its direction cannot exist in this unbound medium. So, then we can take the third possibility in this, that now I have the electric field which is like this, oriented in x direction. It is not constant in this plane. So, it is constant in any of the plane which is passing through this, and without losing generality I can take any plane, I can take either this plane or I can take this plane and assume that the field is constant in this direction. So, I can assume now that the xy plane, the E0 now is a function of z only. So, it is a constant in a plane which is the xy plane. So, I consider this electric field which is x oriented like this, and I assume now that this electric field is constant in a plane containing the x axis, that is the xy plane, and it can have variation only in z direction. So, I have third possibility, case 3, that E is uniform in a plane containing the E vector. And in this case we are taking the E vector which is oriented in x direction. So, it is uniform in a plane containing x axis. So, again without losing generality we can assume that this is constant in the xy plane and it has a variation only in the z direction. So, we can say that your electric field E is some vector E0 which is now function of z only, and it is oriented in x direction. Again we can do the same thing which we did in the previous case. We can go to the curl equation and substitute for now electric field as we did here. However, in this case now, since E is a function of z, the derivative d by dz is not 0, but d by dx and d by dy are 0. So, in this case we have d by dx are 0, d by dy are 0, and d by dz is not 0. I can go back to the same curl equation and substitute. So, I get here x, y, z, d by dx is 0, d by dy is 0, d by dz, x component of electric field is E0z, this is 0, 0, that should be equal to minus j omega mu into h. I can expand this determinant. So, we can see here the x component of this will be minus d E0z by dz. Similarly, the y component will be d by dz of E0z, and the z component will be 0. So, what we see from here, if we expand, I will get the x component from here, that is this minus this, which is 0. So, this quantity is 0. The y component will be plus, the y component will be d by dz of E0z. So, this will be d E0z by dz that is equal to minus or and z component which will be this minus this, which is 0. So, the z component is 0. That is equal to minus j omega mu into h. So, this quantity is 0, x component is 0, the z component is 0, only there is a y component here. So, which gives me now that d is 0 z by dz y component that is equal to minus j omega mu into hx x component plus hy y plus sz z. So, from here we see that the x component is identically 0, the z component is identically 0. I have only the y component of the magnetic field. So, from here I get hx equal to 0, I get hy is equal to minus 1 upon j omega mu d is 0 z by dz and sz is equal to 0. So, if I consider an electric field which is oriented in x direction and if I assume that it is constant in the plane xy, then the corresponding magnetic field is oriented in y direction. But the important thing to note here is the magnetic field exists. In the previous two cases we have seen that the magnetic field did not exist. In the first case we saw that the electric field does not satisfy the wave equation for the time varying fields. So, U are identically 0. In the second case, when the electric field was constant in a plane perpendicular to its direction, did not have corresponding magnetic fields because the magnetic fields were identically 0, and thus the reason the corresponding electric field for time varying fields had to be 0. In this particular case, however, we find that for the electric field which is oriented in x direction and has a variation in the z direction, that means constancy in the xy plane, has a corresponding magnetic field. And since the E0 is a function of z, it is not constant as a function of z, this quantity is a finite quantity. So, we have now the magnetic field associated with the electric field which is x oriented. So, we now have three very important conclusions. Firstly, for time varying fields, the uniform fields in three dimensional space cannot exist. We also see that a field which is constant in a plane perpendicular to its direction also cannot exist if the fields are time varying fields. So, the simplest possible fields which can exist in this medium are the ones which are constant in a plane containing the direction of the field vector. So, this is the simplest solution we get for this problem. Exactly what we did, the plane which we have considered here is the xy plane. In that case, in that plane the fields were constant. We could have done the similar thing for the xz plane also, and we would again get a solution for which the field will be varying now as a function of y, and that's why you will get again the similar kind of expression for the magnetic fields. So, we can say now in general that if the fields were constant in any plane containing the field vector, then perpendicular to that plane the fields have a variation, and that field, electric and magnetic field, will coexist in this medium, and that's why for time varying fields this is the simplest possible solution. Once we get this now, then we can proceed and now try to get the solution of wave equation in this particular case. So, let us now go to the solution of the wave equation with this understanding that I have now the electric field which is oriented in the x direction and is a function of z only. So, let us say now the field which we are investigating, that is my electric field, is now equal to some function of z e to the power j omega t is implicit, and this field is oriented in the x direction. Once we do that, then I can go back to and substitute this field in the wave equation, and that is your del square E, that is equal to minus omega square mu epsilon into E. And since I have only one component, which is the x component, it is the substitute the x component into this. So, this equation should be satisfied by the x component. So, essentially I have here del square the x component is equal to minus omega square mu epsilon into x component. I can expand this del square in the Cartesian system, and that is d2 by dx square plus d2 by dy square plus d2 by dz square, that is operated on Ex, that is equal to minus omega square mu epsilon into Ex. Since Ex is a function of z only now, the second derivative of this of Ex is identically 0, dy is identically 0. So, I now get equation which is d2 Ex by dz square, that is equal to minus omega square mu epsilon into Ex. However, since now E is not varying as a function of x and y, we can as well convert this partial derivative in space as the full derivative, because now Ex is a function of z only. So, we can write down this as d2 Ex by dz square, that is equal to minus omega square mu epsilon into X. This equation now is identical to the equation which we had got for transmission line, because this is now a one dimensional case. We are simply saying this quantity Ex now is a scalar quantity. This is a second derivative in space, that is what we used to get for transmission lines. So, this equation, if I replace Ex by V, I get the equation for transmission line. So, this case, the simplest solution which we get in an unbound medium is a solution which is identical to the solution which we used to get for transmission lines. And since we have investigated transmission lines in details, most of the concepts which we have developed for transmission lines would be applicable in this case also. So, in transmission line, when we were investigating, the first thing we had done was that we had defined this quantity minus omega square mu epsilon, which was in that transmission line case was related to the R, L, G and C. So, we had called this quantity as what is called the propagation constant. With the same kind of understanding, we can call this quantity as the propagation constant for this case. So, we can call this as the propagation constant square, or square of the propagation constant, as we defined there. So, following the notation and convention which we had for transmission line, I can call this quantity propagation constant, we said gamma. So, we can define this quantity gamma square, that is equal to minus omega square mu epsilon, or gamma is equal to square root of minus omega square mu epsilon, that is equal to j omega square root of mu epsilon. if I go by the way the parameters for gamma were defined, which was gamma was nothing but alpha plus j beta, where alpha was the attenuation constant and beta was the phase constant, I can follow the same notation here. So, this propagation constant gamma in this case now is equal to j omega square root mu epsilon. What that means is that for this case alpha, which is the attenuation constant, is identically 0 and your phase constant beta is equal to omega square root mu epsilon. And if you recall, when we were discussing transmission lines, alpha equal to 0 case represented the lossless transmission lines. And what that physically meant was that when the wave travels on transmission line, the amplitude of wave does not decrease, it has a constant amplitude. Precisely the same thing this thing should represent here, that in this case the solution of this equation will be identical to the solution like wave kind of solution for Ex, and the amplitude of this wave should not vary as a function of distance, that is in the direction z. So, this represent now in terms of transmission line and terminology which we have developed, this would represent now a lossless propagation on transmission line. And the solution as we have got for the transmission line case, these are second order differential equations. Once we define this parameter as phase constant beta as we have done here, then the solution of this can be written very easily. So, we can write down this equation from here, that is d2 Ex by d z square plus beta square Ex, that is equal to 0. And the solution of this can be easily written as Ex as a function of z, that will be some arbitrary constant E, we can call that as plus. So, we say E plus x component only, e to the power minus j beta z plus some other arbitrary constant E minus e to the power j beta z. So, on the lines similar to that used for transmission lines, for this simplest case of wave propagation in an unbound medium, we get an electric field which will be combination of these two terms, and we know from our earlier knowledge that this essentially represents a travelling wave travelling in positive z direction. This term essentially represents a travelling wave travelling in negative z direction. So, again we get now the solution for the electric field, which is combination of two travelling waves of amplitude Ex plus and Ex minus travelling in opposite directions, that is in positive z and negative z direction.